Okay, so now that we've got the initial values of both the solid and fluid domains, we're going to go ahead and right-click on Fluid Structure Interaction and go to Solid Mechanics down here, and then click on Prescribed Displacement. So select these two boundaries, and we're going to give them 0 prescribed displacement in each direction. So these boundaries here can't move in the X or Y direction during the entire time of the study. So now we're going to add an outlet for the blood to be able to go out through. So click on outlet, and then this is going to be the outlet up here. So this kind of, in a way, represents the aortic valve. And we're going to set the initial pressure at this boundary as the same pressure of the fluid inside of the left ventricle, which is 11,000 pascals. And then just make sure this suppressed backflow checkbox is checked. So now that we got the outlet, we have all of our boundary conditions set except for the actual boundary load we need to apply to make the left ventricle contract. So we're going to create a time-dependent pressure function, and since there's no direct measurement of the contractile force of the left ventricle when it contracts, I spent a long time just creating an equation, trying to find a working equation that would allow the left ventricle to contract properly. So I won't go over how I actually came up with it. So go up here to Global Definitions and right-click and go ahead and click on, or go to Functions, and then we're going to do a piecewise function. So go ahead and just name it Load, since it's the boundary load. And then the argument is going to be T, which is going to be in seconds, so it represents the time. And then under smoothing, you're going to do a continuous function, and the relative transition size zone is going to be 0.02. So from 0 seconds to 0.06 seconds, the function is going to be 105,000 times t plus 11,000, and then from 0.06 seconds to 0.12 seconds, the function is going to be 60,000 t plus 13,650, and then from 0.12 t, from 0.12 to 0.17, the function is going to be 30,000 times t plus 17,250. And then from 0.17 seconds to 0.19 seconds, the function is going to be 15,000 t plus 19,800. Okay, so now you're going to come down here to the units section, and for arguments, it's going to be seconds. So, and then since this is a pressure function, the units are going to be pascals. So now we're going to actually apply this function to a boundary load. So, okay, so now that we have our boundary, or our equation defined, we're going to go ahead and add that boundary load. So go down to Solid Mechanics and choose boundary load. And then we're going to do a boundary system 1, and then make it a pressure force. And then, so the pressure is going to be basically given the pressure of the function over time. So it's going to be, let's see, what was it, load of t. So that's the name we gave it, was load of t. And then we're going to have to add, okay, so now we have to tell it where we actually want to apply this pressure. So we're going to apply it to this fluid-solid interface boundary. And now we're going to add another boundary load. So basically I had to play with it and fine tune it over time, but I just had to figure out that you had to add more really like specific boundary loads in order to get it to contract right. So we're going to add a second boundary load, and again we're going to make it boundary system 1. We're going to do pressure, and this one's going to be 2,220 newtons per meter squared, and is going to be applied to these 3 right here. And let's see, we're going to add one more boundary load. So just repeat the same steps as before. And this one's going to be 10 newtons. And we're going to apply it to this boundary right there. Okay, now we're going to mesh. So go ahead and build the mesh, and it's going to be the finer element size. So make sure it's finer. And then go down here to study 1 and right click, and you're going to click on show default solver, which I've already done, and click down this arrow right here for solver 1, and go ahead and right click on time dependent solver 1, and you're gonna click this fully coupled solver, which I already did that too. So once you have that set up, go ahead and oh sorry, I forgot, we got to set the time. So make sure it's from 0 to 0.19 seconds, and then the step is going to be 0.01 seconds. So once you have that the time set up, go down to fully coupled 1, and you're going to click compute. And this may take a little bit to solve depending on the computer you're using. I would say anywhere from 10 to 30 minutes, maybe shorter if you're on a fast computer, but that's probably the average time. So I will, there's one more part to this video that's kind of the post-processing and the results, so that'll be the last video though.